In this example, we consider an object that's thrown vertically upward with a speed of 48 meters per second, and we want to answer a number of questions. So the first question that we have is to analyze the motion conceptually by drawing a representation of the object every second that goes by. We want to record the velocity on the picture for each time interval and use the diagram that's provided at the starting point. So actually, we have a picture that's given to us where an object is shot straight up in the air at 48 meters per second at time t equal to 0. And we know that the acceleration due to gravity is negative 10 meters per second squared downward. So what that means is because gravity is present, gravity will cause the object to change its velocity by 10 meters per second every second. So on the way up, the speed decreases by 10 meters per second every second, and on the way back down, it increases by 10 meters per second every second. So if we consider what the speed of this object is, or the velocity after 1 second, the speed or the velocity will have been reduced by a factor of 10, so it will go from 48 to 38. After another second, it will be 28. After another second, it will be 18. After another second, it will be 8 meters per second. So every second that went by, that speed decreased by a factor of 10, and on the way up, the distance covered every second also decreased. So the first 1 second interval, that distance covered is much bigger than the next 1 second interval, and so on. So we get to a point where the time is 4 seconds and the object is traveling at 8 meters per second upward. And the problem is that we can't take away another 10. So we have to find another approach. If there was enough speed here and we could take another 10 away, then the time would get to 5 seconds. But we know that at the very top of the trajectory, the velocity of the object is 0 for an instant in time. So basically we want to know at what time will this velocity reach 0 when it reaches the top. So what we can do is we can actually analyze the last part of the motion in smaller time increments. So once the speed is actually 8 meters per second at 4 seconds, and so here's what we want to know, right? So what is the time it takes to get to the very top where the velocity is 0? So we can imagine examining a close-up of this last part of the motion where the speed is 8 meters per second upward, the time is 4 seconds, and we want to know how much additional time is it going to take to reach 0. So we start off at 8 meters per second at a time of 4 seconds, and we can imagine that if the speed decreases uniformly by 10 meters per second every second that goes by, then every 10th of a second, if we break that 10 meters per second, if we divide it by 10, then that means that every 10th of a second that goes by, the speed will decrease by a factor of 1 meter per second. So that means that after a tenth of a second, so a tenth of that whole 1 second, the speed has decreased by 1. So it went from 8 to 7. After another tenth of a second, the speed will have decreased by another 1 meter per second, so 4.2. After another tenth of a second, it decreases by another second. And we can keep doing that, right? Another tenth of a second, another tenth, and so on, until we get to a speed of 0. And at that point, all those tenths of a second that went by, we eventually reach the top at 4.8 seconds. Now, the time or the distance here is also decreasing every second that goes by, but it's very hard to draw that in this picture. So don't be confused. These distances are not the same. They actually do continue to decrease. So the time it takes to reach the top of the trajectory is 4.8 seconds, and we examine that by sort of drawing a conceptual picture of what's going on every second that goes by. And of course, we're using gravity here as 10 instead of 9.8. You'll notice that whatever the initial velocity is, right here, 4.8 meters per second, if we take that initial velocity and we divide it by 10, which 48 divided by 10 is 4.8, that gives us the time it takes to get to the top. So if we can remember that, we'll also know how long it takes to get to the top. So now we want to examine that same exact picture, and we want to determine the time it takes to reach the top, but we want to also do this by using expressions for acceleration and how acceleration relates to change in velocity. So if we write down everything that's given, we know the initial velocity upward is 48 meters per second. We know at the very top, the final velocity at the top is going to be 0. And we know that gravity is always present, and we use -10 meters per second squared for gravity. And our goal is to figure out the time it takes to go from our initial position to our final position at the very top. So if we use the definition of acceleration, the acceleration measures the change in the velocity, final velocity minus the initial velocity, divided by the time interval. We're assuming we start off at time t equal to 0, so we want to know this time it takes to actually get to the top. If I multiply both sides of my equation by time, it eliminates the time on the right-hand side and multiplies it by the left-hand side. So I'm no longer dealing with a fraction. And now I can actually plug in my values. So I know my acceleration due to gravity is -10 meters per second squared. I'm looking for the time. I know my final velocity is 0, and my initial velocity is 48. So the 0 here I can take out of the equation, right? 0 minus 48 is just minus 48. And I have -10 meters per second squared times the time is equal to minus 48. If I divide both sides by -10, I get -48 meters per second over -10 meters per second squared. And remember earlier I said that if you just take that initial velocity and you divide by 10, of course dividing by gravity, it's going to give us what the time is, and that's the time it takes to get to the very top of the trajectory. The other part to this type of a question is to determine the maximum height the object reaches. So we know that if an object is dropped from a certain height, that the distance that it falls every second that goes by is 1/2 gravity times the time squared. So it turns out that when the object is thrown up in the air, the time it takes for the object to reach its maximum height is the same time it takes to fall back down. And when the object falls back down, it behaves as if it was dropped, because at the very top of its trajectory, its velocity is 0, and so it's behaving just like it was dropped. So if I know the time it takes to get to the top, I can figure out the maximum height by using the fact that that height d is 1/2 gt squared. So this is 1/2 of gravity, 10 meters per second squared, times the time, which is 4.8 seconds, and then I would square just the time value. And so I end up getting 115.2 meters. So a common mistake is to square everything. I would take 1/2, and that's not what we do. I'd take 1/2 of 10, which is 5, and then I would take 5 and I would multiply by 4.8 seconds squared. So as I mentioned a second ago, if we want to know the total time the object spends in the air, which is called the hang time, the time it takes the object to go up is the same time it takes to come back down. So the total time the object is in the air is the time up plus the time down, and both of those times are the same, 4.8 seconds plus another 4.8 seconds. So the total time the object is in the air is just twice the time it takes to go up, which is 9.6 seconds.